Thank you, Kat. So I'll be presenting this architecture of highly available service using Anycast and segment routing in IPv6. Just a little bit more information about me. I'm a software engineer with Comcast. I've been involved in different projects at different layers. I've touched the GDB, trying to make in-house modifications before at one point in time. I've been involved in some content-based routing ad hoc networks, so I know a little bit more about networks, just a little bit on that side. But I definitely have a lot more background as a software developer. And actually, that's the same background for most of the team which I belong to. We named our team Occam based on the Occam's razor. We believe that solutions should be only involve parts that are really necessary, right? So we try to only necessary and not more than that. I definitely would not call myself, say, network engineer in the traditional sense, but I'm very happy for, say, the Monday afternoon panel when it was discussed that, the network can include also professionals that are interested in solving distributed systems problems, which is definitely something that motivated us, our team, to seek a solution this address-based. We were trying to figure out how to improve availability in the many services that we offer in the company. And as we delved into this problem, we started noticing the Anycast as one component that could help address many of the issues that we saw. And also, as we looked into this field, we felt that SRv6 might be a very also provide capabilities we need. From the start, I would like to say that we are not advocating one approach for segment routing over the other. We are definitely users of technology in this field, and we will be very happy to try out different approaches that help us improve the performance which we're seeking. So in this talk, I'll be presenting all these points, and I will be showing how we think all these pieces can fit together and provide a short demo in ContainerNet. So, again, we don't declare ourselves to be the subject matters in this field, and we'll be more than happy to learn from the community. So that, please tell us, if anything is missing, what we have overlooked. All right. So, what do we mean by providing a highly available service? That should be the beginning point. So usually, we have a client make a request, and the server who can answer. That's the normal flow. Now, what happens if the server goes down? Well, then the client doesn't get the answer. So what can we do to address this issue? Well, highly available service. We assume that if the same content or same configuration of the original server is replicated on a second one, then the second one can reply to the service provided that the request can be mapped to that one that is available. By providing this, then the server can reply, and by providing this multiplicity of resource providers, we increase the availability of the service per se, right? So this concept, of course, is used fairly present in, say, a DNS-based global traffic managers, where layer 7 mapping, a client reach out for a FQDN, which is mapped to different IP addresses as they are available or based on certain policy based, right? And not only on layer 7 this is possible, of course in layer 3 it's also possible. A single IP address can be the front, right? And in the back there are multiple different backend servers. So this would be the principle of, say, a local traffic manager that operates at layer 3. Now, when we group this together, this often present architecture for highly available service, right? We have a DNS-based global traffic manager that would monitor different IP addresses for service availability. And these IP addresses are actually not single servers, but they are the front IP addresses of multiple locally available backend servers. So this is one common architecture that we had actually when we started looking into providing highly available services. Now, some of the issues that we at least experienced when we had this was that okay, before. So this would be how this plays out, say in a vast area like US, right? So the FQDN that indicates the resource, right, will be mapped to multiple different IP addresses. In the slide, you can see that on 3 local data centers, they would have different IP addresses. The GTM then provides a geographical diversity for the client to access, and the request would then be mapped to one of the data centers that have local redundancy. Now, so this is actually how usually the service is deployed, right? Now, some of the issues that we have found with this approach, well, it's highly dependent on client behavior, right? A client can cache the results of DNS lookup indefinitely if it wanted. It doesn't really have to obey the TTL field, even though it's advantageous to it to obey. And the problem with this approach is that if, say, the client gets an IP address from the DNS server, then immediately after getting this IP address, the server itself goes down. Then the client, in obedience, compliance with the TTL, will not try to do a new lookup. It will just keep trying, retrying maybe the original TTL, the original IP address that it got, even though there are other servers that are available to provide to answer the request it wanted. So that was one issue that we wanted to avoid. And then, of course, depending on how this DNS resolution is done, oftentimes the policy does not include leveraging the route information that's present. Right? The IP address that's returned can be say round robin, or sometimes the DNS servers will try to establish the latency base, but this is in a sense solving the same problem twice. The routing layer already solved the cost based on a path based on the cost, but we are trying to solve the same problem twice. So that was another issue that we found. And then some groups in our company who use this kind of architecture, they shared how a local DNS resolvers end up being the unit of traffic control. When the DNS updates to a different resolution IP address, say, all the clients that go to that local resolver, then they wholly get shifted, right? So it becomes harder to control the traffic unit. Of course, extension, the DNS or client subnet can mitigate this approach, but well, I guess it depends on whether it's available. And then also, if you can truly aggregate multiple CIDRs or subnets so that it can scale well, right? I mean, those are some of the issues that we have found, and we would like to address them. So, in our understanding, then how could these issues be addressed? Well, one problem of the dependency on client behavior is that once the resource that the client needs, once it gets it, can change over time, right? But what if, right, in this whole stack, we provide, say, an IP address that should always be valid as long as there is a server there that can provide the service. So we go down the layer. We don't use a layer 7 mapping to provide redundancy of resource. We use layer 3. And by using a layer 3 solution, right, we would be actually leveraging already the cost computation that the routers have given us. So that's a thought that we had considered. And for the traffic control issue, we resorted to maybe having gateways that could intercept the packet and forward them to wherever it needed to be. Now, for the first two issues, that sounds very similar to how Anycast would work, right? Say if we have servers announcing the same IP address over different locations, that would be Anycast. Then in a local data center, there will still be a service redundancy, right? But the FQDN, instead of mapping to multiple IP address, gets mapped to a single one. And then this single IP address would be present in all three, say, data centers, or it's a front end up to the service. And then it's at the IP layer, that we will be seeing this geographical diversity. And when a client request goes in, it will be then sent to one of the data centers that that's advertising as a destination for that IP address. Now, then, assuming Anycast works well in that sense, then we eliminate the issue of dependency on the client behavior. And we actually leverage already the information that is present in the routing layer in the network. So we have addressed two issues, but of course, we know that most of the traffic, I guess, right, still rely on TCP for correctness. What would happen to a TCP-based connection in this setup? Well, we have the FQDN that maps to a single IP address that is advertised from multiple locations. And then say a local backend server goes down, then the closest local server is no longer available. A client then request that comes would be redirected to a remote one, maybe. And then what happens then if the closest local server recovers and the route is re-established? This, of course, will break the ongoing TCP connection state. So this TCP connection instability then is an issue that we should solve. And, but then we actually had already proposed the existence of a gateway that can help forward packets as a way of controlling traffic. So in that case, we can then take advantage of this solution, this approach that we had already proposed, and use that to track connection state for TCP. So then the question then becomes, if we need to have servers that can dictate how traffic will go, how can we make that happen? How can we direct traffic on from a machine, a server that we have? Well, that's when we looked into segment routing, right? As mentioned, I'm just going to go briefly since we had already talked about segment routing. But segment routing is essentially extension to the routing extension header that essentially we push into the IPv6 header a list of segments, and those nodes that support the segment routing conform to the list and send packets accordingly, right, to the path that's specified by the list. In a sense, it's a source-based routing, right? So say, how does that work? Just very simply. Say the original path from node S to D goes through X and Y, right? If you just say source is S and D is the destination, then this will be the path that the packet would follow. But with segment routing, then the source can say, no, I want the packet to go through SXZD. When this happens, when this is set, then the packet goes through S to X. X will look at the segment and say, oh, the next hop that the packet must go through is Z. So for sure, the packet will go to Z. It may cross Y, but for sure we know Z will be present in the path. Then Z will look at the segment and say, the next one is D, so I will just send to D. So in this setup, the nodes that are in between this S, X, X, Y, Z, they don't need to know actually segment routing at all, segment routes. Only these nodes that are participating need to be able to process the segment routes. And then if this is the case, then we have found a way to manipulate traffic, to force them to go wherever we want. Of course, we are focusing on IPv6, right? So how that would work? Say, the same scenario, the local backend server goes down, it's no longer available. The client request goes to look for the IP address, but because our gateways are still up in that locality, the packet will still be forwarded to the closest, or say, the result of the Anycast route. And our gateways then would forward the packet to a remote cluster. I mean, this slide, maybe I put the map, the first map on the top to imply that it's just a lookup, right? So the client is still talking to the closest, and then we forward to the next. And when the local cluster recovers, our gateways keep the state of TCP connection, and they continue any data exchange still towards the remote server. But of course, any new incoming requests can just be served locally. So that's how our architecture will work. Now, then, when we put all the pieces together, this is how it would look like. Say in a data center, this is how things could be. We have a bunch of hasher gateway nodes. These will be peering, like BGP peering with a local router. They announce themselves as the destination for the Anycast IP address. And they will also take any incoming flows, generate a hash, and send it to one of the second layer, the router elements, the OG router. The OG router is the element then that will keep track of the connection. It's this connection information then is it's duplicated between a primary OG router and a secondary OG router, so that if the primary goes down, the connection information is retained on the secondary, and the TCP connection can keep going. Then on the back-end server side, we would be running an agent. An agent would be an eBPF filter that's running transparently to the application, but it's on the same host. And they can actually remove or add SRv6 headers as needed. So they could send responses back to the router, OG router, for connection tracking purposes, or send response directly to the client. So this is an overall architecture that we envision that would improve the availability. So if this is architecture, then how do we see it working, say, for a TCP connection? So bear with me, this packet animation, there are a few glitches here and there, but say a client sends out SYN packet. It wants to talk to the service IP, get a request. Then it will just set the destination to be the service IP, the Anycast address. The packet would then go to the hasher, which is the destination that has been set. The hasher then will add the segment route to the packet and send to the local OG router based on the hash result. The OG router monitors the local backend servers and say, oh, I have actually a backend server available. So I will update the segment route list, and then I will send the segment to the agent. The agent grabs the packet at XDP point before sending it into the kernel. So it's able to see, oh, it's a new connection. I will add an entry to my connection table. I will strip down the segment routes, the extension header. It just becomes a regular IPv6 packet, and I send to the kernel. And the kernel will then forward the packet to the application. Once the application responds, the same agent then will grab the packet and see, oh, this belongs to the flow that I've been tracking. So what it will do in this initial TCP/3 handshake, it will add a segment route to the response packet that will send back to the OG router, so that the OG router now knows, okay, for this flow, is that backend server that I need to send a packet to. So this then goes to the OG router, and now the OG router has the connection information. It will take this packet, strips the segment route, and make the packet just like regular IPv6 packet without segment route, but from the source address of the service IP, and send it back to the client. So in this way, the client, he just sent a SYN packet to the service IP address and got a reply back. Then the client will usually acknowledge SYN ACK, three-way handshake, and this ACK packet then follows the same path. Go through the OG router agent, and the agent sends the ACK from the client to the application, to the kernel. Now, what happens then for an ongoing TCP connection when data is being transferred? Say the client wants to fetch some data, then the packet originally goes to the hasher, and because it's the same TCP flow, the hasher will send to the OG router, and the OG router, add the segment route and send to the OG router. The OG router will then take a look at the segment route and decide that, okay, it needs to go to the agent. And the agent will do the same thing. We'll take the incoming packet, strip the segment route, and send to the application. Now, when the data from the application comes back, it looks up and says, oh, this is not a connection establishing. I assume the OG primary and secondary routers have already the connection information. I can just send the data back direct to the client. So in this way, we preserve the semantics of TCP connection. So using these segment routes and the agent PPF. Now, why do we need all that, right? So, well, consider if there is a failover that's needed. Right? So in this, so far, we've only seen animations on the east side of the slide. What happens if, say, a sync packet goes through the hasher node and the local server is unavailable? Well, the hasher will still send to the OG router, but the OG router now, noticing that the local is unavailable, forwards the packet to the remote cluster. It will go through the remote cluster hasher. The hasher will update the segment list and send to its own local OG router that will then notice, oh, I still have a backend server available. I can send it to there. Now, in this slide, I've shown east and west, but nothing prevents, say, you have more, east, west, central. One could imagine this packet can traverse and find, quote unquote, the best data center to answer this request, policy-based. Depends on how we want to set how this packet will respond, right? Not simply just a one failover, but we can incorporate elements that dictate how an incoming request should be answered. So, but continue our example, the agent then here will know exactly how it should, it will just strip the segment route, go to the application, grab the response, and then it traverses back. It goes back to the same path it came from. So the local OG router knows that the packet can be forwarded to that one specific remote cluster, and the connection is tracked also in the remote cluster. And then, of course, this SYNAC packet is sent back, and the ACK response will then go the same way, same path, right? So the ACK can come and will go to the the same thing will happen, add a segment route and send back, and the ongoing data transfer will follow the same path. But in the same way, the GET will go to the local, which will be then forwarded to the remote. And at this point, because the connection has been established, this agent then can choose to will respond direct to the client, because there's no need for tracking this connection. So that's how we would envision. And I don't have the packet animation here, but at the close of a TCP session, during the exchange of a FIN packet, then these connections can be cleared from the connection table, both in the OG router and on the client side. Right? So in this way, we preserve the semantics of TCP for the client. We hide the failover details to the client. And we can keep an ongoing TCP connection even if the local backend server recovers, right? So we allow failover, but as I have mentioned, failover we can just consider as a specific instance of a policy-based traffic management, right? Because our OG nodes act as gateways to incoming traffic. Because of the SRv6 or segment route, we control exactly how we want this traffic to go. So we can shape the traffic based on the needs of the backend server and create policy profiles for traffic management. So say when incoming traffic to local cluster is 90%, start forwarding traffic to remote cluster, right? So that's actually something that we can incorporate, and it doesn't have to be to this one specific failover. You can split across multiple, right? And then this connection would all be tracked. And of course, as I mentioned, failover would be, say, cluster capacity drop to 0. Any new incoming traffic is forwarded to remote cluster. So that's how we envision this architecture. It definitely does not address the issue that we have seen. Now, I mentioned our background is software development. We collaborate with the network team in Comcast so that we can actually try out our ideas and test. We are currently trying to set up a lab so that we can test this idea. But to say sort of as a proof of concept to our vision or architecture, we actually enable this setup in ContainerNet. Now, what is ContainerNet? It's a port of Mininet that supports running Docker containers as nodes in a, I should say, their virtual network. All right. Now, I did a recursive definition, right? So what is ContainerNet? It's a port of Mininet. So what is Mininet? Mininet is defined as a network emulation orchestration system that allows us to run a collection of endpoints, nodes, links, switches to provide an instant virtual network on your laptop. It does this by using network namespaces so that you can create nodes in the laptop to emulate the presence of a host. And it uses VF pairs, virtual Ethernet pairs, to emulate links. Right? So it has a Python API that allows us to create a network from the scratch and set up the links and the switches. The switches are usually implemented by running like an open flow controller so that the switch element is a learning switch. And one advantage is that the software is run as is, right? It runs against the real Linux network stack. So that's how our development, right? So we did the code and we can test against the Linux network stack. So one advantage that's listed by ContainerNet is that, say when TCP/BBR was released as a Linux module, you could run in ContainerNet, all right, Mininet, right? But of course, because it's an emulation on a local machine, you cannot emulate, say, speed higher than is possible by the underlying hardware, right? You cannot do that. It's bound by physical laws. Unlike a simulator, right? A simulator can simulate things that are different, but the emulator, you hit the capacity limitations of the physical hardware. And it's Linux only, and it only supports Ethernet links, but it served our purpose. We were able to use ContainerNet to test our ideas. So how do we develop? Our OG nodes, hash and router, we're actually using a DPTK for fast packet processing. We developed using Rust. So all the packet animation, actually we already implemented using this NetBricks framework, right? It's based on DPTK. We are actively working on refactoring NetBricks to suit our purposes. And hopefully as our project matures more and more, then we'll be sharing with the community and hoping to get feedback. The agent, as I mentioned briefly, was implemented using eBPF, was a code written in C, and we loaded to the nodes using BCC. So it's a filter that runs on XDP, Express Data Path, on the ingress, and a TC on the egress, right? So all this actually is the real code that is run in ContainerNet. So in the routers in the ContainerNet demo that I'm going to show, they run like old routing software, Quagga, Zebra, BGP. And for peering, for our OG hash nodes to peer, we run Go BGP Docker. So ContainerNet, right? So we actually run, we make containers and we emulate them. Like we use, in ContainerNet themselves, we use something called Docker Compose that can bring multiple different Docker containers and run them on top of a Docker container to emulate the same layout that we would have, say, in a real bare metal server. So actually, like for instance, in one of our hasher tests, we just push out a Docker Compose YAML file, and we grab the containers, and we can just bring them up. So in the same way in the bare metal server, in the same way in the container, in ContainerNet. And currently, in our demo, we actually run console for health check and status. And in today's demo, we'll be showing a dashboard that was generated by having our clients and servers emit like stats to an InfluxDB node, and we visualize it via a Grafana dashboard. So this is just an introduction to the ContainerNet demo. So next, I'll be showing the video. So say in our topology, right? So we say make run. So this will bring up the Python script. You can see through here that it's trying to go out and pulling the containers. And this video was sped up a little bit. It's not as fast as this, so that I've saved a little bit of space in the presentation file. But this is how it can happen, right? So nodes are brought up. They are up the different commands that apply to them. See, we can list here all the different nodes that are there. The OGH is our hasher nodes. OGR are router nodes, and then east and west, right? So in this demo, we're gonna show a failover. So the two routers, R1 and R2, in the same layout of the slide. And when the OGH container is brought up, the Go BGP container pairs with the BGP running on the R1, R2, and we can establish connection and announce the routes for our Anycast IP address, and then have it set up. So then we will start also the monitoring nodes, and then the InfluxDB and the Grafana nodes, so that we can visualize on the dashboard. This is the end result of the dashboard. So you can see that on the top we have a client, we track client, and on the bottom we have one hasher node, and I already scrolled down to 3 router nodes, and then the agent, which is the backend server. In this specific, we have then an east and a west dashboard, right? So right now there's no traffic. I just wanted to mention that in this specific topology scenario, our client is not emitting stats to the dashboard, so we'll not see any stats from the client side. I have another video that will show. But then now we need to start the traffic. We wrapped, so these are actually all commands that we use via a Docker, right? Because there's all Docker containers that are running on this Vagrant machine. So, but we wrap them using the scripts, and the failover 2 means that we send one curl, one HTTP request every 2 seconds. So we can see that this client is on the west side, so it hit the server on the west side. That 2001.558 is our Anycast IP address. Now we can see data flowing. The hasher these are short-lived curl HTTP requests. So each one is a different flow. These flows get spread by the hasher to the multiple OG routers, right? So that each one will be tracking the connection information. So, for scalability. And then these connections, they will all go back to the same backend server, because in this topology, we only brought up one. But yeah, so this is just to show that the traffic is spread, in a sense, evenly among the 3 routers. And then it goes to the backend. Now, next, what we need to do then is to stop the backend server that is running on this current cluster. So, yeah. Oh, yeah, then to confirm, right, there's currently no traffic going to the east side, because the Anycast would attract all the traffic to its closest cluster. So now we need to then stop the west, a west server. And once this west server client is stopped, we should see the response coming back from the east. And but however, the packet would still flow through the hasher and the routers on the west, because connection is still moving forward in that direction. It's being tracked, right? The agent will, so there was some delay in this stop command, so that's why it's not as fast as we would like to be. We are definitely looking into how to improve this process. But the overall what happen is that during this time, when the backend server stops the server, so finally it responded, then you see that there was on the left side of the screen, there was an empty response. This is the time when the console, the health check did not detect that had failed. But immediately upon detection, the east server response came back. So in this way, we can see that it's no longer dependent on the TTL. The client just keeps making requests, and it's up to how fast we, in the service provider, can detect the failure. Once the detection takes place, the route is immediately can be sent out to the server that's available, right? And then on this side, we can see that the traffic started flowing to the east cluster, flows through the east routers, and is getting serviced by the east side backend server. Now, I mean, I don't have a long-lived TCP connection example here to track, but just these short-lived ones, if we start the web server on the west, then the traffic will shift back to the west, right? So that's how this would happen. Now, and then yes, again, all depends on how fast we can detect a change of condition in our network. We no longer need to rely on client behavior to address availability issues, right? So let me go to the next video. In the second video, I skipped all the initialization part. In the second video, we're going to show a long-lived TCP connection and how that long-lived TCP connection will survive, say, the router going down, right? So we talked about how connection is tracked by two routers, primary and the secondary, and how this connection will not be broken even if one of the routers go down. This recovery script will create a TCP connection, and on this TCP connection, it will send HTTP requests that will keep the connection open, right? So it's one TCP connection that is and then HTTP traffic is flowing on top of that. So because it is just one connection, the hasher will take this flow and map to just one single OG router, right? But we see a blip on OGRW2, sorry, on one of the left ones. And in this scenario, we provided 3 backend servers. This blip is a packet exchange that took place to coordinate who is the primary, who is the secondary. So we know that through this dashboard that the primary is getting all the incoming traffic, and there is a secondary that can serve as a backup. So in this case, let's try to bring down the primary router and see what will happen to our open TCP connection. So eventually, what we will see is that the client side, which is using a socket, like a Python client socket that select to check on incoming packets, it will not break. The throughput of the client may drop a little bit as TCP gets maybe experiencing more delays because of the shift on the primary and secondary, but the connection will be held constant, right? So we can see here that it dropped a little bit the throughput, but overall it recovers and the connection does not break down. So in this way, we have verified our implementation in ContainerNet, and we are actually, I mentioned, we are trying to move towards a lab in our in our company, so that we can test this in a real like a bare metal system. So in conclusion, in today's talk, I presented a common architecture for highly available service that addresses issues we have found in a DNS-based system. And we definitely wanted to bring Anycast and IPv6 together. And we believe that provides clients, in our solution, we provide clients with the closest available server, and we leverage the network layer to provide proximity. And the speed of failover is as fast as detection of the down local server. Right? As we have seen, once the detection of the local server happened, we're immediately able to switch traffic to an available server to answer requests. And traffic forwarding can be policy-based. Our segment route approach allows us actually to reach all available clusters where the server is available, so that like depending on how we decide this traffic should be, the client request should be answered, we can pick which data center to answer the request based on any policy we like that might be having like previously decided. So thank you. So I have some time for questions.
Hi, Aldrin. You mentioned server failure and OG router failure, but what if you have a long-lived connection? It's coming in through site 1 and needs to move over to site 2.
Oh, you mean, say, if there's a local failure?
Yeah, your advertisement to the internet from one site goes down. Right, you end up with another OG hasher, right?
Uh-huh.
But that OG hasher has no state about the flow.
Right.
What happens then?
Well, I mean, so you're saying if our OG hasher nodes go down, and then the route somehow is withdrawn, or?
Yeah, the route is withdrawn from one side.
So if the route is withdrawn, then yes, there's nothing we can do. The TCP connection will be broken.
Okay.
Right.
Yeah, that's a problem that a lot of operators have. That's
right. I mean, yes. If we are like our assumption is that say the load balancer service is up while the backend server goes down. Yeah. Right. So in that scenario, yes, we can definitely address outages. But if our load balancer service goes down, then yes, any ongoing TCP connection will be broken.
In that case, the Anycast advertisement to the internet doesn't help.
So the Anycast, any new incoming request would be directed to an available like cluster, right?
But you'd still break the connection if you had to flip sites.
Well, so of course, yes, any ongoing connection will be broken, but any new ones will go to the remote, and that will be capped for as long as our OG service is up, right? Even if the local cluster recovers, that one will still. That's a good question. Right. Okay. We'll definitely look into more into that.
Hi, thank you. This is Mike Timonero of Verizon. Just curious, the motivation for all this is to preserve client to server or cluster stickiness?
To what?
To preserve the stickiness, right?
Yes.
Between the client and the server.
Right.
So that means you looked at your traffic profile and found most of it needs to be, that stickiness needs to be preserved, and you have long-lived TCP sessions.
Right.
Is that it?
Yes.
Okay.
But yes, we use this to preserve TCP sessions, but we want to use eventually to shape traffic, right? So say we want to eventually, like depending on the capacity, we want to allocate however much traffic that can be forwarded.
Okay, thank you.
Yeah, you're welcome. All right, if no more questions, thank you.